Welcome to a lesson with Dr. Powell. Let's yet again continue this example with this matrix that's acting as a scalar. Okay, we've discussed how this guy right here is a zero matrix, and we've talked about how row and column operations should still preserve the representation of this as the zero matrix, um, and that's column-wise. Now let's ask a question here. Can we find a polynomial scalar that acts on the vector so that you get just the zero vector out of this? So this is really the zero vector here, always for any v. So in other words, it's like when the polynomial acts as a scalar, you can think of it as being representable by this matrix, p of x times the identity matrix. So you're multiplying with p of x in each component, where this will always be representable as a zero vector with a p of x scalar in each entry right here. Is that, can we find a polynomial that does that? Well, what we're going to do is we're going to start with this one, which we know, this matrix, which we know is representable as the zero matrix. And that is because each column here is representable as the zero vector. It's not entries, it's just columns, remember that. So we do some operations. So here, for instance, we can swap the rows here and then negate that row. So change its sign. So change the sign of this as it pops up there. So we get a 1. So it's kind of like what we're doing for Smith normal form at, over fields as we go. We want to get a 1 up here. But remember that we can never divide by polynomial, just multiply. All right. So we're going to we got a 1 here. Then what we're going to do is we're going to use this 1 and we're going to airdrop going down here to zero that out. To do that, we have to multiply this row right here by negative quantity x minus 1. Now, when we do that, so just think about that, negative x, so negative x multiplied by x minus 1, but then we have to negate that, so it'd be like this. So it's x squared minus x is what we're adding down to that 1. That's why we get this. X squared minus x is that 1 down there. Okay. So it's looking fairly good. We got a column that looks like 1, 0, 0. We can use this and airdrop this way freely as we will, as long as we can we can multiply it by any polynomial we like, since we have a 1, and we can zero that out. So we zeroed that out that way. Now we have this, and we want to get a 1 here. That would be nice. We can do it by swapping. We swap and multiply by a negative. Get this. Okay, so we got a 1 here. Now, let's try to get this down to 0 here. So let's airdrop with a column, or with a row, that is. So multiply this row by x squared minus x plus 1, and then add it down. And so this entry with that would give you that, and down, we engineered it so it would give us a 0 there. So this is good, because then we have a 0, 1, 0. And here we can airdrop this way to clear that off freely without anything else changing. And so we end up getting this. In fact, this is a Smith normal form here, with dealing with our module instead of a field, but we still got something very much like it. This actually is what you'd call the minimal polynomial, because let's call this p of x, because if we were to write it out like this, notice that this matrix right here is actually the product of these two matrices. You could try this out. I mean, okay, so if you put this column into this function, it's like p of x times it, so you get out that column. And if you put in this column, so if you put in a 0, 1, 0, it picks out that. If you put in this, it says p of x times that. Hey, it gives you this, right? Now notice that this matrix is this one which you just found, which is the zero matrix, which means when you multiply with the zero matrix, you only get the zero matrix. So this is the zero matrix. In fact, this is the minimal polynomial that can actually do this. I mean, if you tried x minus 1, or if you tried x squared minus x plus 1, it's not the zero matrix if you work it out. This is the minimal one. in fact just kind of using a thought, which you don't need to know necessarily here in our context, but I'll add it anyhow, just food for thought. So all polynomials that act like zero actually make up what's called a submodule. It's kind of like a subspace, subvector space of this, but it's not really. But this isn't a vector space; it's a module, but it's the same idea. It's an additive subgroup, and scalar multiplication is closed in it, so we call it a submodule. But and submodules of this guy right here, this is actually also a ring. Because it has really nice multiplication and addition and all that. That's together. So it's even more than a module even. And any submodule of such a guy is actually called an ideal. Okay, well that's terminology we don't really necessarily need. However, due to the fact that you can have polynomial long divide really nicely in here, especially since R is a field, that makes it nice here when we look at polynomials with coefficients in it. Actually, every ideal is just like multiples of something. It's like you pick one thing and all the multiples of it, can make up the ideal. There's one thing that will do that. And at least give or take, you can multiply it by any scalar that's like any real number and it still works. But there's a minimal one. The minimal one is the one that everything is a multiple of, in fact. And in the next video, we'll look at another example where we'll look at another example which kind of talks about that a little bit more. But at least for our case, we've succeeded in finding this polynomial, which we will call the minimal polynomial, that actually works kind of like multiplication by zero. Thanks for watching.